We see steel literally everywhere, but have you ever stopped to think about how one single metal can have so many different personalities? Well, inside this super common material is a secret world of tiny structures, and today we're going to unlock its secret identity. So here's the central mystery, right? How can steel be soft enough to bend into a paperclip, but also hard and sharp enough to become a legendary sword? I mean, it's the same basic material. The answer isn't really in what it is, but in how it's made. And that leads us right into our first section, steel's secret recipe. And you'll be surprised, it's actually pretty simple. It's just iron and a little bit of carbon. But, and this is a big but, there's a crucial rule that changes absolutely everything. This right here is the golden rule of steel. Think of it like you're in a kitchen. It all comes down to two things. Your ingredients, that's the iron and carbon, and your cooking method, how fast you cool it down. That combo of recipe and process is what gives you the final product. Okay, so before we can start making our steel, we really need to understand its main ingredient, iron. And it turns out iron has a couple of different personalities or, crystal structures that are absolutely fundamental to this whole process. So, down at the atomic level, iron atoms can arrange themselves in different patterns. The two we really care about are body-centered cubic, or BCC, and face-centered cubic, or FCC. Just think of them as rooms of different sizes. The BCC room, it's pretty small, not a lot of space for carbon atoms to hang out. But the FCC room is way more spacious. And here's a great little memory trick for you. FCC equals full carbon capacity. So how do those different rooms even come into play? Well, it all starts when you heat the steel up. This creates the perfect starting point, a single, uniform structure that all other forms of steel are born from. You could call it the mother structure. So meet austenite. This is steel in its hot, super malleable phase. And because it has that FC structure, remember, full carbon capacity, it acts just like a hot sponge, easily dissolving all those carbon atoms into a perfectly uniform mixture. It's soft, it's ductile, and it's basically the blank canvas for everything that comes next. And if you need a really easy way to remember when austenite exists, the name itself gives you a huge clue. Just think, austenite is formed at heat. Simple, but pretty brilliant, right? So, we have our hot austenite, this perfectly mixed soup of iron and carbon. Now comes the most critical step, the part where we forge its final character. And it all boils down to one thing, cooling speed. From that one starting point, that austenite, we can take three completely different paths. If you cool it down nice and slow, you get one thing. If you cool it incredibly fast, a process they call quenching, you get something totally different. And yeah, if you go for a speed somewhere in the middle, you get a third option. Let's go meet these three characters. First up, we've got perlite. This is what you get from a slow and steady cooling process. This gives the carbon atoms time to move around and organize themselves into these neat, alternating layers of a soft phase and a hard phase. The result is a really balanced material, kind of like a chocolate wafer. And here's a great memory trick. Perlite is a pair of two different things. Now, what if we do the complete opposite? A super fast quench, like plunging the hot steel straight into water or oil. The carbon atoms have absolutely no time to move. They get instantly trapped right where they are. This creates martensite. It's like water flash freezing into brittle ice. It's incredibly hard, and its name basically says it all. Martensite gives you maximum hardness. And our in-between character is bainite, which you get from a medium cooling speed. It's stronger than perlite, but tougher and way less brittle than martensite. The source had this great analogy. It's like semi-frozen ice cream. Not quite liquid, but not quite a solid block of ice either. It lands right in that sweet spot. So we've forged these different characters. But what if one of them is just a little too extreme? For example, martensite is super hard, but it's also really brittle, which isn't always what you want. Luckily, there's a way to fine-tune it. And this is where tempering comes in. You take that ultra-hard martensite and you gently reheat it. This isn't about transforming it completely, it's about relieving some of that internal stress, letting a tiny bit of carbon move around, and basically trading a little of that extreme hardness for some much-needed toughness. Tempering that martensite gives us two more refined structures. Reheat it a little and you get sorbite, which has a softened bite, taking that edge off the brittleness. Heat it a bit more and you get true state, which finds a true balance of strength and toughness. These are kind of like the final touches that customize the steel for its perfect job. Okay, so we've met all these complex characters that are formed through heat treatment. But if you look closer, they're all just different mixtures of two pure, basic ingredients. So let's meet the fundamental building blocks of this entire family. On one side, we have ferrite. This is pretty much pure iron, with that BCC structure that can't hold much carbon. Think of it as soft clay, very flexible. Then on the other extreme, we have cementite, which is pure iron carbide. And just like the name suggests, it's hard and brittle, like cement. Every single structure we've talked about is just a different mix of these two basic things. And this table just brings all our main characters together beautifully. On one end, you've got the soft and ductile ferrite. On the total opposite end, you have super hard and brittle martensite and cementite. And right there in the middle, you find those balanced characters like perlite. It's the entire family tree of steel, all in one spot. And to help you remember this entire cast, here's a fantastic mnemonic I found. Friendly, clever people always make better, strong tools. That's ferrite, cementite, perlite, austenite, and so on. It's a brilliant way to keep the whole family in order and really lock in this knowledge. So there you have it. We've kind of demystified steel. It's not magic, it's metallurgy. It's just a recipe of carbon content and cooling speed. From a paperclip to a sword, it's all about controlling that inner structure. Which leaves one final question for you. Now that you know the recipe, what kind of steel would you create?